All right, everybody, let's talk energy. Energy is our new unit, and we begin actually with some definitions of our different flavors of energy. This began in class with a few demonstrations with some toys, and it became pretty clear that we needed to clarify a few of the types of energy before we could go much further, because energy seems to be in many forms, and if you want to define it by the object you're talking about, many times you find things that repeat. So what we found when we looked at this is that we had four key types of energy. So let's start with our first one. We call this one kinetic energy, and this is our energy of motion. So when is this energy present? When you have an object in motion. If it is not moving, there is no, that looks like one word, although we know it is not, right? But we need to have some velocity in order for that to work. The equation is fairly straightforward. It's 1/2 mv squared, and if you look at the way that's designed, you'll notice that the mass is important, but the velocity is more important because you square the velocity. Therefore, the faster you go, if you double your velocity, you'll quadruple your kinetic energy. If you triple your velocity, you'll have 9 times the amount of energy. And that's kind of important, especially if you're dealing with objects moving very fast, because if you are going to stop something moving very fast, you have to get rid of all that energy. And that's a conversation for another time. Some key things we figured out about kinetic energy is that it is never negative. You cannot have a negative value. And I mean, if you look mathematically at it, it makes sense because this is a squared value. So even if you had a negative velocity, which is directional, you'd square it and lose that. You cannot have a negative kinetic energy. That is not always the case when it comes to some of these other ones. All right, the next big one that we looked at actually had to do, and I'm just going to space these out so I have some room to move. This one's called UG, or sometimes if you see something old, they call it PE, and that is considered gravitational potential energy. Now, this particular type of energy we were showing with using a bowling ball, a ping pong ball, and a baseball, looking at dropping them on people and what would make you the most nervous. And it was pretty clear that the mass of the object made a big deal and the planet you're on. If we were on the moon, dropping a bowling ball wouldn't be nearly as scary because little g is much, much less. So when is this energy present? When you have a mass, that's pretty easy. That's everything. But this one's the important one, when you have a height, when you're actually off of some 0 point, which we realized is arbitrary, and so we set it wherever it makes our math easiest. And if you're on a planet, which again is all the time. So, and we will not be leaving Earth anytime soon for a field trip, so this should not be something that we are changing all that much. Our relationship is direct and linear. All three of them are equally weighted. All right, some key things to note about gravitational potential energy is that we pick where the height is 0 to make the math as easy as possible. And that usually is fairly obvious, but you can have a negative potential energy. So don't be shocked if you see an occasional problem where it doesn't seem that intuitive, that you end up with a negative value for potential energy or a negative height. That's not a problem, but you do usually pick your height so that it is easier for you to, to work with it mathematically. It's totally up to you. Our third one is another type of stored energy, and this one comes up quite a bit. It's a spring. The key thing about a spring is, let's say that's a spring, and let's say that's the length of the spring. In order to contain energy, what we noticed is that your spring either has to be compressed or extended beyond its normal, beyond this. Okay, so when is this energy present? When you have a stretched or a compressed spring. Just a spring sitting around not doing anything does not have stored potential energy to it. Okay, the equation we're working with is 1/2 kx squared. This is one that we're actually going to derive in the lab. All right, and just some quick reminders. It's been a while since we've seen these. Right, but this is what's known as the spring constant, and x is the stretch or the compression. Not the length, but the change. All right, and that value is squared. Our last one, which can be a little bit tricky, let's go back to blue. I like blue. Is thermal energy or heat. Okay, the main thing that we need to realize about this is that we lose it. Once we lose something to heat, we can never get it back and use it for something else. The other thing that's kind of interesting about this is that it is only a change. There's no actual formula that we can just say, oh, this is how you calculate it every time. That's not true. What you look at is you look at what you should have gotten and what you really got, and you take the difference between the two. So there's only a way for you to measure the difference from what you should have had, basically what you've lost. So this one can be a little bit tricky because we have another way to express it. Okay, so keep in mind, sometimes we call this something else, and we'll look more at that in a bit. All right, and this term is work. And when we lose things to heat energy, we say that that work is being done by the friction. All right, don't use it twice. You have to classify it one way or the other, but not both. Okay, so keep that in mind as you go. All right, so once we defined our flavors, that's kind of boring. There's not a whole lot we can do there, but we can do much more interesting things when we start looking at changes in energy. So these are 3 examples that I picked from practice number 1, which is on page 144 of your workbook, in case you're trying to find it. All right, these are the pie graphs. Now, pie graphs you probably haven't worked with since like 2nd grade, but that's okay. What we're going for here is a visual representation of what's happening to the energy in each snapshot of the motion. Then what we'll be able to do is take this and eventually get to a point where we're doing mathematical computations with this. But for now, we just want to make sure we can identify and see what's happening to the different types of energy as we go. So we start with pie graphs, and this is the first example that we began with here, good old number 1. All right, so this is our picture over here, and as you can see, we have a dot and then an arrow and a longer arrow. Those are our 3 snapshots. So list the objects in your system. So which objects have energy or can transfer energy? We're talking about the ball, all right? And then everybody wants to say the earth or like the ground, but really, or no, actually what everybody wanted to say was gravity. And I said, well, what causes the gravity? The earth causes the gravity. So that's the main thing. And we did this twice. We did this once, just assuming we're dropping like off the table in the classroom, and once we're dropping it off the Empire State Building, in which case we would have air resistance to worry about. Okay, so the first thing we did, well, we did this twice. I will do the ugly one that we did up top, and then I'll fix it. All right, so the main thing you want to do when you've got your pies, all right, you got your circles here, is ask yourself, okay, what do I have that, you know, what do I have each step of the way? So when I look at this very first one right up here, the very first ball right there, ask yourself, what kind of energy do I have? Do I have kinetic energy? No, because I know that my ball is at rest, so it's not moving. All right, so there's no kinetic energy there. I don't have a spring, so there's no spring energy. I don't have thermal energy because thermal energy is a change, and well, we're at the beginning. There's no change yet. So the only energy I have is gravitational potential. You know what, now that I think about this, I am not going to even need to do it this way. I'm not going to put this extra one up here because I did it a little differently in the classroom. I'm just going to put my circles right in here. We'll do this quick. So no kinetic, no spring, no thermal because we're not changing. That means we're only left with gravitational potential energy. When we get to the middle, Do we still have gravitational potential energy? Yes, we do. Do we have more or less of it? We have less of it because our height is less. It's closer to the ground. And we're moving. So some of that potential energy became kinetic energy because we can see by that arrow that we have both. So I cut it in half, and you don't have to use half. It's actually not quantitative right just yet. So half, 2/3, 1/3, it's all good. At the bottom, we're assuming it is right before it hits the ground. It has no more potential energy because the ground is our 0 point, but it is going as fast as it can possibly go. So it all changes to kinetic. Now this is more interesting to me because I can see that there's a transformation of energy, and I know what I have at each point in the motion. If I do this with air resistance involved, well, I still have the same beginning, but what changes is that I get a change, and some of that change is due to the air taking energy away. We take energy away from the kinetic energy, right? So actually, realistically, let me fix this. All right. My gravitational potential energy didn't change from the previous example up here. What's going to happen is that air resistance is going to take away from the speed. So I'm not going to have quite as much kinetic energy as I did before. And this is usually how I put thermal energy in there. Okay, that's the loss. And I black it out because I can't use it for anything else. When I just did that backwards, didn't I? Why didn't y'all catch me? Let's try that again. Third time's a charm. Okay, so let's try that again. My height is still going to be... No. Oh, wait a minute. No, I had that right. Never mind. My height is still halfway. I was thinking of a different example is what happened to me there. All right, so there's my E thermal. Okay, now at the bottom, I should have more air resistance, and I should have, some kinetic energy there. My kinetic energy is getting bigger because I'm getting faster, but it's not quite as much as my previous problem before. Okay, so hopefully you see the difference there. Didn't make that too messed up. So then this one, number 6, this one is an important one, I think, because it shows a ramp, and there's some ramifications there. And it depends on where you want to make your height 0. But this is a great example for that. So what's in I've got a spring in here. I've got a cart in here. And you notice they don't tell you anything about friction on the surface. That is totally up to you. You can do it with friction, you can do it without friction. I think I'll say that there's no friction for now, because why not? All right, so we have the spring, the cart, and we have the earth, because we're going to be dealing with some height in a few minutes. All right, so now if I look at this, my first pi, my second pi, my third pi. So let's start at the beginning and the end, I think. At the beginning, I'm not moving. Right? If you look at the picture, it's definitely not moving. So I don't have any kinetic energy. I'm basically on the ground. Right? You can decide, maybe you want to say, oh, it's a little bit up on that ramp. I got a little bit of height, but that's fine if you say that that's your height 0, so I don't have any potential energy. That means all of my energy must be spring. Right, because my spring is compressed, it's getting ready to launch this cart up the hill. Then it starts to go up the hill, and I can tell that it's moving, and I can tell that it's moving, so I'm dealing with kinetic energy. The spring is no longer compressed, so there's no more spring energy, that's gone. But the question in the class was about height. I mean, do you measure the height because it's going up the ramp, or do you measure height this way because of the vertical rise? And I'm here to tell you, it's always the vertical rise. Okay, do not worry about the fact that it is going up the ramp like that. Okay, so the second one, we have a little bit of height, and here we have even greater height. So we definitely still have potential energy. Okay, now again, up to you if you want to go half and half on these, or if you want to split it in some other amount. All right, but you should realize that we are we have stopped, and we've got that height. So everything else here must be UG because, again, the spring's no longer compressed. Our last one here, the piece of clay being dropped to the floor. I'm going to change colors, I think. Would be nice. So we've got the clay. Again, we've got the earth. That's why it's dropping. Up to you whether you want to talk about air resistance. I'm going to say no, it's probably not that high. So if you look, again, in our first pie, it's not moving because we have a dot. In our second pie, it is moving because we have a dot, or because we have an arrow. And in our third one, we have a dot, which means it's not moving again. So at the top here, there's no spring. So we don't have any spring energy. At the beginning, we don't have any kinetic energy. That leaves us potential gravitational energy. Makes sense. All right, on the way down, we have kinetic. There's still no spring. And I don't have quite as much, I don't have quite as much potential, gravitational potential energy. So again, you don't have to necessarily go half and half on these. The one at the bottom was what really threw people for a loop because you're actually hitting the ground on this one. So let's think about that. You don't have any more UG because you're on the floor. You don't have any more kinetic energy because it's not moving. You don't have a spring. So what are you left with? You're left with thermal. That seems weird, but those are our choices. Those are our 4 key types of energy. And let's face it, all of that energy has left the system. So the only way to explain that is with the splatting on the ground, really. So we're going to clean that kind of an example up in just a minute. So today, what we started to do is look at a new representation. And this representation will help lead us to math, which is great because, you can draw all the little pie graphs you want, but if you can't solve a math problem and figure out how fast something's moving, you're going to get stuck in a hurry in physics. So same ideas with snapshots here for the pie graphs. You've got a beginning, right? You've got something going on here at the beginning, and you've got something going on here at the end. These are what I like to call LOL diagrams because of the shape of the graphs, right? We've got, actually, it looks like 2 L's with an O in the middle. All right, so if you're wondering where that crazy name came from, that's exactly where it came from. I'm going to give myself a little bit of room there to work. So what you're going to do, what you did at the beginning for pie graphs, right? This part right here, where you listed the objects in your system, we're going to do the same thing, but we're going to put it in the middle. So for this one, we've got a spring, we've got a car, we've got the earth, and you notice they tell you that this one is a frictionless track. That means I don't need to worry about friction. I don't need to worry about energy loss that way. Since I'm not going to worry about it, I'm not going to put the track in as part of the system. This is not worth it to me. Okay, what I've got here at the beginning, I have, let's go through them one at a time. Is there kinetic energy? No, there isn't. Put an X to show me that you've actually decided that. Gravitational potential energy, there's no height. Makes sense that it's not there. Spring energy, well, that's a compressed spring. I'm going to give it 5 boxes. That's just an arbitrary number. Don't worry about it being 5. That's just me. All right, so that's my beginning. My snapshot final. When I'm up here, well, let's see. There's no thermal energy because I have no friction. There's no spring energy because the spring is no longer compressed. I have some combination of potential energy and kinetic energy. So let's say they're even-ish, or well, maybe not. All right, let's go 3 and 2. All right, so 1, 2, 3, and 2 there. Okay, so that one seems to work. The brilliance of doing the LOL is now I can come up with a conservation equation, all right, for the beginning and the final snapshot. So what I'm going to say is that the spring energy from the beginning is equal to the kinetic energy plus the gravitational energy at the end. And if I get numbers, I can actually work with that and come up with a numerical answer for something that I didn't know before, which is awesome. So you can see we did several of these. And in fact, there was another one, but I'm just going to work with these 3 so you can look at the differences between them. So what do you do when you have some friction? Well, as you could probably imagine, you're beginning here. Let's see, we've got our spring, cart or car, the earth, But now we also have the track because of the friction, right? So we've got all of those things in there. At the beginning, it looks very similar. We don't have motion, we don't have height, right? Let me just double check if I've got the right ones here. Yep, UG comes first. And then I have spring energy. So I was thinking maybe because I'm so close to the board and I don't have my glasses on that I couldn't see. I was reversing potential gravitational spring, but I'm not. Okay, now the main difference here, of course, is that we're going to have some thermal energy. So let's say you have 2 with thermal energy. The question is, where does it come from? Does it come from the gravitational potential energy or does it come from the kinetic energy? Well, if you compare this height to this height, you can see they're exactly the same. So if you use 2 blocks before, you should have 2 blocks again for gravitational potential energy. It's going to come off of the kinetic energy. I'm just going to leave it like that. I know that's not perfectly lined up with the dotted lines, but it's just slightly non-calibrated here, so you just have to bear with. All right, look at the number of boxes versus where the little dashy lines are for me. Conservation. Spring potential energy equals kinetic plus gravitation plus E-therm. Now remember, there's no formula for thermal energy, but if you can figure these out, you could just do a little subtraction and you could find it with no trouble. So what's going to happen with our next one here? Same as the first time, but we take our final snapshot earlier, meaning the card is only halfway up the slope. Okay, so what I take that to mean is we are back to not having any friction. So there's our little system, right? And we've got our 5 of UG, or I'm sorry, of US. I said that wrong. Right there, those go. Right, and then at the end here, you'll notice I'm not going as high this time. So if I don't have any friction to worry about, and I don't have any spring to worry about, then I must be worrying about UG and K. So before I had 2 for UG, let me make that 1. Again, don't look at the dashed lines, just look at the number of boxes I've drawn. And then the other 4 be kinetic. Right? That adds up to 5. So we would still be conserving, but it would be just distributed a little bit differently. Our formula looks very similar to the first one, but mathematically, if you did them, they would be different. So hopefully the LOL diagrams kind of make sense. So these 2 examples, I have them, I copied them twice because there's 2 different ways you can do this and 2 different ways you can look at it. And I've left a little space over here for some of the notes that we ended up taking in the class. So Superman is stopping a speeding locomotive and it's pushing him backwards a few meters in the process. All right, so if I go to do this, what I'm going to notice, of course, is that yes, I have kinetic energy to start with. No, I don't have gravitation because it's not off the ground. And no, I don't have spring. So let's say, I'll just do 4 this time. I guess I'm out of room. Okay, whoops, I forgot to do the beginning first, the middle part, right? So we've got the train. I'm not going to write locomotive. I can't fit that in there. And then I've got the ground, right? Because we're talking about Superman stopping it. Now this is the first way that you can solve this problem. And maybe you've got Superman. Superman. Okay, now eventually let's think about what's happening here in the final. Velocity is 0, so that means I don't have any of this, right? I don't have any spring energy or gravitational energy because I don't have height and I don't have a spring, which tells me that all that kinetic energy became thermal. Nothing wrong there. That's supposed to be 4 squares, so they match. So we could write the equation like this. And there's nothing wrong there with that. And look, even though you don't have a formula for E-therm, in this case it's equal to kinetic energy, and you do have a formula for that. So you could find it if you needed to. Now here's the other way that we describe it. We describe it as Superman doing work on the car. So what we do to show that there is a transfer of energy into or out of the system thanks to Superman is we do this instead. There's a train and then there's the ground. And Superman's out here. He is out of the system. And energy leaves the system by doing work. And notice I have that whole right-hand side of the screen because we're going to explain what the heck I'm talking about in just a minute. So let's go to this. Kinetic energy, we've got 4 of those. We don't have gravitation, we don't have spring. We don't have kinetic, we don't have gravitation, we don't have spring, we do not have E-therm. You know why? Because it means exactly the same thing. So our other way to describe this would be to say that kinetic energy equals work. So what is this fancy work thing? And how is it related to E-therm? I'm so glad you asked, because it comes down to our basic fundamental understanding of what energy is compared to work. So what I like to do is use the analogy of money, because most of us understand money very well. All right, so if you think about it, if I have, and you don't have to write this down, but if I have $1,000, right, and I put that in my checking account, well, you know, I could have a savings account, and I could move some of the money over there, right? Like maybe I did 500 and 500. Or maybe I have CDs, and then I could move some of the money, like maybe I'll make that 400 and I'll put 100 over here. But all of these are storing my money. Like if I need that money, it can all go back in my checking account and away I go. I still have the original amount. So what we're talking about is a storage unit for money, right? My checking account is a storage unit. That's what energy is. Energy is all about storage. We've got a couple different ways to do it. We've got gravitational potential, we've got kinetic, we've got spring, and we've got this nebulous E-thermal, which we keep talking about. All right, and I'm going to put a star by this one because this is the one that we have to be careful with. All right, but all of these are ways for us to store the energy that we have. Now, work, on the other hand, is a little bit different. So let's say, for example, again, I have $1,000 in my checking account. And then I have to go and get gas. Well, that's going to cost me money. Let's say over a couple of weeks I spend $100 in gas. So now I have $900. And then I go to Target and I get a whole bunch of junk at Target and I spend another 200 bucks here. Well, now I'm down to 700. You know how this goes, right? Before you know it, you're down to nothing. Until this magic payday happens. Payday! And you get more money in your account. Hooray! And then you start over again. So you're putting money in via getting paid. You're withdrawing money and losing it to all these other places that need your money, like the grocery store and the gas station and whatever. This is a transfer mechanism. That's what work is all about. Work is all about either adding energy in or taking energy away. Okay? The thing that gets confusing is that it's the same value numerically as this one, but I'm getting ahead of myself. All right, so this is transferring. All right, we either put energy in or we take energy out, rather like your debit card, and we use it for something else. In order to do work, you have to take a force times a distance. That's the idea of doing work. So the point being, let's say you're driving in your car and you have a lot of kinetic energy and you smack into something. All of that energy, if you stop, has to go somewhere. Well, it's going to do work. You could argue it's E-therm, but unless you're screeching into the, you screech to a stop along the road, I would argue that probably not. If you crash into something, you are going to apply a force over the distance of the hood of the car, the metal of the car, maybe you, depends on how much energy there is to dissipate, right? But you're going to have to apply a force over a distance. Again, let's go back to what we learned in momentum. Crumple zones, airbags, all of those things are safety measures because they are taking that energy and breaking the car with it by doing work over the distance of the car. If it does not do that over the distance of the car, that energy goes somewhere and it goes into breaking you driving the car, which is a bit of a morbid thought, but the energy is going to go somewhere. So it's better to ruin the car than to ruin the person inside the car. That's what safety is all about. My point, though, is that these two things, they are the same. They are just a different way of looking at them. Do not use it twice. You got to pick one or the other. You don't get to use both. I'm not going to say work and etherm in the same formula. That doesn't make sense to me. Okay, you can't account for the same quantity twice. So be careful about that. Here's our last one. So we keep talking about being able to do some math. So let's do some math, shall we? All right, and let's see how we can use an LOL diagram for this. Now, for the most part, it looks like we can just, we're using the LOL diagram to identify our energy types in our initial snapshot and our final snapshot. That has actually always been the hardest thing for kids to figure out. It's the math, once you've got the formula, has usually been relatively easy. So this technique of using LOL diagrams is so that you correctly identify the energy transfer, and that's important. Okay, so let's take a look. We've got a block, spring. How much is the spring compressed? None of the energy is stored as thermal energy. Okay, so no friction. We're not going to worry about the floor. It's all good. So we've just got two things in our system. As we're going along here, we've got some kinetic energy. I'll just go with 3 this time. Why not? We do not have any gravitational potential energy because we don't have any height. And then here we're going to compress this. We don't at the beginning, sorry, I'm getting ahead of myself. Here we don't have any spring energy. When we get to the final snapshot, we don't have any motion, so we don't have that. We still don't have any height. Now what we've done is we've taken all of that kinetic energy and come up with some spring energy. So if I write my equation, that's pretty easy. Now, you notice we got some numbers in here, so let's figure out what we're talking about. Kinetic energy, if you go back to the very first page. Spring energy, if you go back to the very first page. All right, let's cancel that and that. I like to stick to variables without throwing in numbers until the very end. Divide, because we've got multiplication going on over there, so that'll cancel. And then we're going to just square root that. In order to find it. Now that I've got that, I'm just going to go plug and chug. All right, so I'm going to do the square root. The mass is 8. The velocity is 5, so we're going to do 5 squared, all divided by k. K is 50 newtons per meter. So this on the top, 25. 25 times 8 is 200, divided by 50. We're going to square root that. So that's going to be the square root of 4. Which, as you know, is 2. So 2 meters is the compression on my spring. So it doesn't take me long to figure out what the compression on my spring should be. All right, so these are some of the techniques that can help you out when it comes to setting up conservation. We've got a lot more to go, but that is a great way to start. I know that these LOL diagrams, they don't call them the same thing in MOPS, but they do have many of these. So we will be able to use this technique to know what is going on with energy. So thanks for listening. Make sure you come in if you need help.